By the way, I'm gearing this whole thing up to where I can record the review for the exam. That way you can look at the review a couple of times. Okay. Oh, there it is. Okay. Okay. All right, what we're going to talk about here, and we talked a little bit about this before as far as the correlation goes, okay, is this is the relationship that exists between two variables. Generally, it's at least up front, we'll be talking about the x's and the y's, okay? The relationship between an independent variable and an outcome variable, all right? A couple that we've talked about before is the most normal one is you have time is the independent variable, and sales is the outcome variable. And so the way you figure that out is, does time determine sales or does sales determine time? Obviously, time is more of a driver for sales, so here sales is the formula for these variances. Right. And what I'm doing here is I'm going back and I'm using the way you work on this, example. The way you first do this is where we had a covariance. Help me here one real quick. Right. Anybody and that's called the variance of x and y. Oh gosh. What was that example? Anybody got that? What was that? Cat and dog. Whatever it was. But anyway, so we just plug in the variables. We calculate sigma that we've already determined was the standard deviation. Okay, and sigma is nothing more than the square root of sigma squared, which is the variance. So we determine the variance. And what you have here is you have the standard deviation of x and y, and the standard deviation over the standard deviation of x times y. And that gives you the correlation between these two variables, x and y. Was it cat dog? Yes, I think it was. You're right. Yes, that's right. All right. Yeah, it was cat dog. Okay. So the different options that were available, or the different numbers that were available here, and all you do is you just plug in those numbers. Okay. And what you'll be given on the exam and what you'll be given in real life is, because it's going to the computer's going to calculate for you, or you're going to know this based upon previous history. Okay. And so you just plug those in, and so now here's what you get. Okay. The correlation between x and y is 0.954. Great. Right. Now the question becomes, what does that mean? And so I ask, what does that mean? If you know your correlation is 0.954, what does that mean? I'm going to give you a hint. All right. If correlation, relationship, I think somebody before used the term, were they linked, or how much influence one had over the other. Okay. And I'm drawing on the board here, and I'm drawing a line, and in the middle is 0, and on the end, on the left side, is -1, and on the right side is +1.0. All right. Now, if you see a correlation that's 0, what does that mean? If that number were 0, what does that mean? There is no correlation. That's exactly right, Casey. It means no correlation. Okay. Now, taking that thought, okay, what does it mean when you start approaching 1 as a correlation? Very strong. Right. That's exactly right. So you have very strong, and sometimes you'll see relatively strong when they get down to about 0.5, 0.6. Somewhat strong, okay, and this is the way statisticians talk, okay, somewhat strong when you're down around a 0.2, all right, and so what that means is not only is it very strong, but is that relationship positive or negative? Positive, exactly, okay, and so you have the same situation on the left side of 0, where there's no correlation, and it becomes a very strong negative correlation. And the way that slope looks is just like we've talked before. I'm going to draw a little, okay, draw that thing here, draw the x and y. So here's y, here you have x. And so this is a very strong positive correlation, right? So this thing is actually going to look, it's going to have like the steepest slope you can possibly think of. It's going to look like that. Okay, very steep slope. So whenever you see a strong correlation, you're going to get a slope that is off the charts. Anybody ever been to snow skiing and a black diamond, a double black diamond, or what they are, the suicide hill or whatever? These are even worse than the suicide hills. Okay, I mean they're like cliffs, straight down. All right. Okay, now if you see a correlation that's somewhat strong, okay, and that would be about, what would you say somewhat strong would be? 0.75. Let's say somewhat strong. Yeah, probably about a 0.3. So you would see a slope that looks a whole lot less steep. Okay, but it would still go up and to the right. All right. All right. Now, and if you see a slope of 0, boom, that just goes straight across. Right. Correlation is not the slope, but they are the formulas within slope are part of correlation. Yeah, yes, they're very tightly intertwined. And you can think of the slope as more of a let me think. You can think you know what you can think of correlation as more of a ratio to understand what the slope is really saying. Loosely, it's a little bit of a Schulteism, so be careful. But you can kind of make that association between the slope and how large of a number that is between 0 and 1 if it's a positive slope. Okay. So now let's extend this one step further, slightly further. Is what would happen? Where would you be if you saw a slope that looked like this? Yeah, which side of the 0 would you be on then? To the left. That's right, exactly. And so that'd probably be a slope. It would be a nice slope. That you'd probably see a slope about 0.7, 0.8. Okay. So you're looking down the hill. Okay. You'll see that again. I assure you, in about 3 weeks. Okay. So what I need for you to do is go to 525D, and I'm actually going to give you the standard deviations. Okay. And I'm going to give you that the standard deviation, and these are sigmas, so they're x's and y's, they're sigmas, so it's of the population. And so you see that you're going to have a long math problem. Again, I'm not overly interested in how well you do mathematics or algebra. I'm mostly interested in, can you take what you calculate or is given to you in your report and figure out, well, what's going on there? All right. So what I'm going to tell you is that sigma of xy equals 87. Okay. Sigma of x is equal to 7.81. Okay. And sigma of y is equal to 11.4. And let's call that 7.8, just to make this a little bit easier. Right. That's an 87. 87. Yes. That's a standard deviation of x and y. Okay. It's just part of the formula. Okay, so the question that Tanner brought up was, okay, so what does that mean? Is that a 98%? And it's like, no, it's not a 98%. What that says is there's a strong correlation or strong relationship between X and Y. It might be time and sales, or it might be advertising and sales. It might be what the temperature is outside and how many ice cream cones are consumed. Whatever that relationship is between X and Y. And so Tanner's question was, well, does that mean it's 98%? And it's no. It's a relative number. Okay. And remember the scale we had 0 to 1, 1 to 0, 1 to, or 0 to minus 1. So what you do a more valuable number becomes R squared. So if you square, and this is going to be a very, very powerful number as you begin understanding statistics, because if you square that up, what is that? 0.97 times 0.97, what is that? 80 something? What is it? Oh no, it's, what is it, 0.95? Okay. Now I can begin moving toward Tanner's question that says 95% of the reason why the Y outcomes occur, 95%. So now we can talk percentages, not necessarily probabilities, because we can still talk probabilities, a whole other subject when we get into here. But you could say that 95% of the reason Y occurred what is accounted for in X.
So you could use that like, say you run a business and you put, X amount into marketing.
Yep.
Would be your Y value.
Yep. And you can actually determine statistically what is influencing sales. And that's what, kind of bringing it to back to the strategy of a corporation or the strategy of a company, large or small. If you're small, you have investors. If you're large, you have Wall Street, okay, that are investors, or the analysts, okay? And so what you need to begin understanding is, as anybody inside an organization, certainly at the CEO, president level, if you're a small business, the president and the CEO are probably one and the same sometimes. But you need to understand what influences sales. Okay? If you, as the owner or the CEO of that business, or the president, or even the CFO, the vice president of marketing and sales, whatever the case might be, if you don't understand what drives sales and what drives profits, what's going to happen to you eventually? Yeah, you're going to be pursuing your excellence elsewhere. Yeah, that's exactly that, and that's kind of a nice phraseology to say. The other one is you'll be spending more time with your family, and you're 45 years old, right? And it's like, oh boy, that's not the reason. So, and much like think about, and again, I don't want to disparage any local corporations, but there is a CEO. There are CEOs after CEO. In fact, there's a CEO today. I assure you, out of all the companies on NASDAQ and Dow Jones Industrial Average, there's a company right now whose CEO is being terminated because he doesn't understand R squared. He or she does not understand what drives their revenues or their profits. Okay? That's how powerful that number is. And so then you can get not only an R squared for X, but you can get R squared for X1, X2, X3, because profit and sales are made up of many, many different variables, right? That's why that becomes such a very important concept as time goes on. But the key here right now is that that there is a strong relationship between X and Y, between the antecedent, the input variable, and the outcome variable, which is Y. All right. So now I want to talk about binomial, the properties of binomial. There are four. Let me go one more here. Okay, good. Okay. Binomial just means there's two outcomes: success or failure. Yes or no. Sí y no if you're in Spanish. Net y ya, net y da in Russian. Whatever language you want to go with, there's two outcomes on each trial, okay? And the probability on that success is denoted by P, all right? And the probability does not change from trial to trial. So when you flip ahead and you flip ahead and you flip ahead, the probability is always the same. Whereas I'll show you another example later on or another situation later on, where if you don't have this probability of success, and there is a change on each additional outcome or test, you can't use binomial, you have to use something else. And also the trials are independent, meaning that one outcome does not influence the other outcome, okay? If you flip ahead, in theory, if you flip ahead, all right, or you flip a coin and you get ahead, okay, and it was a 50%, what was the probability that you're going to get ahead on the second one? 50%. There's no relationship. Now, you get 10 heads in a row, Okay, now you're going to go, well, wait a minute. I think there's some influence here. But in theory, there is the first head or the first tail has no effect on the second head. They're independent events. Okay, it's pure serendipity, pure luck, pure chance. Okay. All right. Oh, hold on. Okay, we're back in action. Hopefully I don't do it again. Happy trigger finger today. All right. So binomial probability distribution. Okay. All right. So we're interested in how many successes we get in n number of trials. You're going to have 25 trials. How many successes are you going to get out of 25 trials? Are you going to get 1? Are you going to get 2? Or are you going to get 3? Okay. And so X is the number of successes occurring in those trials. So it's an N and an X sort of discussion. Pretty simple, basically. And here is the handy-dandy formula, okay, for the probability of the binomial probability function, okay? And you're going to see here, hopefully a little bit more comes up. And what you're going to see here is our old friend, right, the number of experimental outcomes. Remember this formula? N factorial over x times n minus x factorial, okay, from before. Number of possible outcomes, okay? And now we're going to multiply that times, we're going to add a second component here, and we're going to multiply that times a probability associated with the binomial nature of the outcome. And that formula goes as follows. Okay, hope that comes up. There we go. All right. And that is, I'm just going to read this just to make sure you understand it. And it's a probability of a particular sequence of trial outcomes with X successes in N trials. So you have X number of successes, you have N trials, and you plug it into this handy-dandy formula, okay? And you come up with your binomial probability distribution. Or actually, let's be more specific, is what is the probability that the value of X is going to occur, okay? Or X successes will occur in this case. Let's take an example, okay? All right, they're worried about a low retention rate, okay? They've seen a turnover of 10%, all right? And so they want to estimate the probability at 10% that a person will not be with the company next year. So they're going to choose from all the hourly employees, and they're going to have to give me did they say how many employees were yet? We'll have to get the number of employees. You have your probability here, 0.1, P, okay? You're going to choose 3 at a time, which is your X, okay? And then we're going to have to be given an N. So the probability that the first employee leaving and the third employee staying, okay? So it's an S, F, F, okay, is the way that comes out. All right, and so here is the actual calculation. All right, so there are three outcomes, okay? They can stay, okay, leave, stay, leave, stay, leave. Leave, stay, okay? And leave is the failure. And so you just plug that into that formula, the handy-dandy formula that you had before over on the right-hand side associated with the probability, but you have one additional step here, okay? Is you have to insert the probability function, which includes a discussion or a scope of this analysis that says, okay, how many possible outcomes were there? And that's why it gets moved over to 2.243. Okay? So here's basically what you were given in this problem. The probability was 0.1. N, okay, you had 3, and X was 1, okay, of one success. All right. So you had all these names, okay. N was 3, okay, and you pulled them out one at a time. Okay. Okay. All right, so now what I want you to do is hit B, 531 B, E, and D. Just do B, E, and D. Don't do all of them because I've got to, this will get much easier for 2 reasons. One is this binomial probability distribution table has been, there's been tables that have been created for all the different situations that can come up, and I'll show you how to use that. And also within most of the software, probably all the softwares, there's a binomial distribution probability that will calculate for you as well, and all the tables are already preloaded. Okay, and we'll do the same thing for Poisson in a few minutes. All right. So now, let's take a look at the example we had before. Evans Electronics, and we're going to use a decision tree. There's another way to look at the same problem. Okay, decision trees. Again, if you're a visual, if the way you understand situations is through visualization, decision trees are your tool of choice. Okay, because it just kind of easily comes out and makes sense. So here's leaves and stays. Okay. All right. And it'll just build up. Get the probabilities come up. And there should be one more column here. Yep, there we go. All right. All right, so here are your probabilities. You see here, it's a leave and stay. Binomial. That's why it's called binomial. Okay? You leave or stay. First worker leaves. Second worker can leave or stay, and then that trees out to a third worker that can leave and stay. All right? And so when you plug those formulas in, you're going to get 0.01, 0.09, 0.009, or 0.001, 0.009, 0.8, 0.081. Okay? And these numbers will eventually add up to 1. Okay? Because this is everything is in there. All right? So that's the decision tree. Make sense? And it's a real easy, just a binomial. Boom, you go leave, stay, and then you run the stay side, and the next person stays or leaves, and then you have the probabilities that you run at the end. Okay. All right, I'm going to, let's forego 531A. I think you can do the decision tree on your own. And what I want to go to next is there's handy dandy tables in the back of the book. Okay. And you'll start using these tables, using these tables more and more as we go through the next couple chapters. You'll see T distribution, Z distribution, but it's Appendix B, and the binomial tables start on 985. Okay.
So you can just look these up?
Yes. And it gets even better than that, is that if you put these numbers into maybe I'll demonstrate that on Thursday or something, just as a kind of a sideline on Thursday, but you can actually put these into the software and it just does it for you. Okay. And the reason we do this, to kind of give you the ground level up, or the basics up, is that way you know what the theory or the actual formulas are in behind what happens on the handy dandy tables. And normally, you're right, you're going to go straight to the tables, T distribution. You're not going to calculate the T distribution every time, or the Z distribution, or the binomial. It's just not going to happen. Okay. All right. And even the tables aren't necessary at this point, because basically what they've done is the tables in the back that start on 985, they try to anticipate every type of combination between the the probability and the n chosen x at a time. And it's like there's it would be a book that wouldn't even come close to being like, what is it, 4 or 5 pages here, right? It'd be I don't know, it'd probably be a book bigger than there's room for all the different n's and x's that are possible out there. Okay. All right. So not only are the tables unnecessary, or not only is the formula unnecessary, but the tables become obsolete as well as you move into the software side of the house. Okay. All right. Okay. So what I wanted you to do is go to Appendix B 985 in your textbook, and if you don't have one, I think Appendix B is the same in the older version too. Just go to Appendix B in the older version, okay? And you look up N is 3 and P is 0.10. And that's probably going to be N is 3. 0.10, 0.09, there it is. 3 and 0.10, right? And you'll see a 0.243. Yeah, you'll see that. All right, so you'll go to page 988, okay? And all you do is you look up the p-value. The tables are driven by the p-value across the top, okay? And then you have to do the combination of the p-value, which in this case was 0.10, okay? And n, and then x at a time. Okay, and then it'll just tell you what the probabilities are for each one of those choices. So you don't even have to use the tables. You don't have to use the tree diagram. Just a nice way to quickly move toward the understanding what is the probability for a certain situation. The other thing that it gets a little bit better than this when we get into the Poisson. But so what you can do from here? Does everybody have that? Was everybody able to find that on page? You would have had to go to, was it P.10 and 3 and yeah. So it would have been on page 988. Does everybody see how we got that? Does everybody see the 0.243? You choose it one at a time. Yep, one at a time at a P.10. The P.10 is across the top. It's way in the upper left-hand corner. Is where on page 988, look way in the upper left-hand corner, and you'll see the p-value. The probability is 0.10. Of a success, okay? And then you'll see n, and then choosing, what's the probability of one success out of n outcomes. Got it? And that ends up being 0.243. Okay? Got it? Okay. Just look for 0.243, and then you can kind of reverse engineer back into it. So for 531C, okay, 531C, all right, that we decided was a 0.36. What do we say, 0.36? If you calculate that out, yeah. Just verify that on the table. And not at p equals 0.6, but at the p-value you used for that one, which was, 0.4? Yeah.
Is this table pretty universal?
This is an absolute universal table. Yeah, absolute universal table. Somebody, what happened here is somebody created these tables for you, okay? And here again, the table not only has running the formula become obsolete, now the tables are obsolete given that given that these are all loaded in the computer. Now, if you ran that at 0.6, you would get another value, right? Everybody, what value would you get at 0.6 if you ran it at 0.6? What would you get there? Yeah, 0.16, right? So if you had a probability, okay, of success of 0.6, now your probability, your overall probability would go down. All right. Just as before, you can calculate your expected value, variance, and standard deviation. I'm going to home in on exactly what you're going to need here right away. Is all you're going to do from this point on is figure out what your expected value is for the mu, or for the actual number, okay? And that is the calculation. You should take n times p, okay? What was the n on yours? 2. What was the p? 0.4. So it was 2 times 0.4, so it would have been, it'd be 1.8, it'd be 0.8, that's right. Okay. In this example, it ends up being 0.3. Shoot. Sorry about that. I thought I had it on airplane mode. Okay. Telemarketers always call at the worst time, don't they? Okay. All right, and if you ran that out, but the real value here is 0.3 employees. That would be the probability that you'd get 0.3 employees. Now, can you get 0.3 employees? Not really, but statistically, you can get 0.3 employees, and so you'd manage to that number. All right, and so as we talked, what's the expected value of x at 2 trials? Okay, and you just go 2 times 0.4 from the example problem that we had before. Okay, and that'd be a 0.8. Okay. All right. All right. Let's hit Poisson. This is an intriguing sort of probability. Okay, because what you do here is we're cross-cutting. Okay, we're cross-cutting frequency with time. Okay, so where before we had x and y, and neither one of those were time. Now we're saying, okay, what happens when you introduce time? And these are used in multiple situations. In fact, let me think. We do that here, okay, in the university. All right, we have a person at the front desk. Anybody ever met Brenda down there at the front desk? Brenda down there at the front desk. Okay, and we have to figure out how many calls are going to come in. And what's the probability that we're going to lose a call if she's not there between the hours of 5 and 7? You can actually calculate how many people are going to call in from a probability perspective based upon the Poisson tables. It's called Poisson, okay? And it was, the guy's name was Simeon Poisson from, like, I don't know, 12 BC or something. At any rate, so, and they're discrete random variables, okay? And they can be an infinite number. So 0, 1, 2, discrete. All right. So let's go through an example here. All right. So here's a couple of number of knot holes in linear feet. Okay, linear feet is in some respects a time or a distance parameter. The number of vehicles arriving at a toll booth in 1 hour. Anybody been through a toll booth? Anybody ever been in a line at a toll booth? Okay, somebody has calculated that they needed, using Poisson distribution tables, somebody has calculated how many toll booths you needed in order to satisfy 90%, let's say 90% of the demand that comes through those toll booths. Okay. This is kind of my home turf. My home turf is Bell Labs. Bell Labs was the previous AT&T, or it was a part of AT&T in days gone by. And we would actually size phone systems, and we still do that today, or that is still done today. Everybody has a cell phone, right? Okay. Everybody has a cell phone? Okay, man. Yes. Yeah. That's why they got them. No. Everybody has a cell phone. Okay. If everybody in this room picked up their phone at the same time and tried to dial, what might happen? Okay, if everybody in this entire building picked up the phone at the exact same time, what would really likely happen? You wouldn't overload, but a lot of probably about 10%, maybe a little bit more, the calls just wouldn't go through, and it would force you to redial. Okay, and that's because back at the cell tower, okay, and these might be old terms, but they have what's called a mobile telephone switching office, and it keeps track, and it has only a certain amount of channels that can come through on the specific radio frequency that you're using on your phone. Okay, and some engineer sat down and said, okay, we're going to need 124 channels to serve Batavia. Okay, now does that mean everybody in Batavia will never have a drop call? No. Okay, that means they're going to probably engineer that thing to about a 0.9 on the Poisson table when you take time and users. Okay, in a call center, anybody working a call? Who works at the? Oh, here we go. I assure you, at the Best Buy. Best Buy? At the Best Buy. Do you have 50 people? Are all 50 people always there at the same time?
No.
No. They vary that. And there's a reason for that, because how many customers do you get at noontime on a Saturday?
A lot.
A boatload. Okay. How many people do you get at noon on a Monday?
Very few.
Yeah. And so they have staff using these Poisson tables to figure out how many people they need in that store given any specific time. And everybody has their schedules, and there's some guy, and it's not even some guy, they just probably plug it in based upon the number of clicks that they see coming through the front door. Okay, they keep track of all that, and they will staff up accordingly. It's really a cool probability distribution. You can apply it to almost anything that has time associated with it. Okay. You have equal lengths. Okay, so a minute to 2 minutes is always 60 seconds, right? An hour is always 60 minutes. Okay, 1 hour to 2 hours is always 1 hour. All right, so that's what they mean by equal length. Okay, and they're independent of each other, so one does not influence the other necessarily. Although when you see a bunch of people lining up for the new iPhone, there might be an influence there. All right, as far as time goes, because everybody goes, oh my goodness, they're getting together for we haven't seen World Series tickets here for a while, but as soon as everybody sees the World Series ticket line forming, everybody forms up. So you wouldn't be able to use Poisson here. You'd use chaos. You'd probably use chaos mathematical theory there. Okay. So here's this function, handy dandy function. Okay, same way as before. All right, as far as we're just going to plug and chug, but you got to know what each of these numbers mean, okay? And so X is the number of occurrences that you're going to examine within an interval. Here's the probability, and here's the mean number of occurrence you normally get in an interval. Okay, the value of E is just 2.71, much like pi, okay, 3.14, okay? And then it's X factorial, which is the factorial of the number of occurrences in an interval. The trick here is to get all the time intervals the same, or all the distance intervals. You could do distance as well. The distance interval is the same. So you can't do meters and kilometers. You can't do meters and feet. You can't do can't do half hours and seconds. You have to get everything in the same unit of measure. Okay, within the grouping of those measures. All right. There's no stated upper limit. Okay. And so eventually that number is going to get large enough where your probability is going to be 0. So for example, let's take the Best Buy. Okay. What's the probability that 10,000 people are going to walk in the door between noon and 1 on a Saturday?
Not very high.
That would be almost 0 to none. Unless you've got the new iPhone coming out or something like that, right? Or some. I mean,
I think we would be hard pressed to find 10,000 people in the area.
Oh no, I said 1,000. Did I say
Okay, good.
1,000? Yeah. There might be they've had them. I mean, certainly in places where they had 1,000 people lining up for the new iPhone, right? Okay. All right. And so, from a practical standpoint, okay, any additional examination of the value of X becomes moot. Okay, it just doesn't matter. Okay. And so let's take a hospital example. Okay, I assure you that a hospital, especially an emergency room, has kept statistics. And I was reading an article the other day where statistics and business analytics were going to be the primary driver of all things healthcare in the future. Okay, least of which is the example of an emergency room. Okay, an emergency room doc probably costs, I don't know, $50 an hour. Maybe let's call it 50. Let's call it maybe $100 an hour. Okay, do you want 2 people who are making $100 an hour there when you only need 1? Of course not. Okay, but if you get 3 people or 4 people or 5 people coming in the emergency room at the same time, is 2 docs going to be enough? Maybe. But if you get 40 people in at the same time, 2 docs aren't going to handle it. Okay, so you have to staff up accordingly. Telemarketing centers do this all the time. Inbound customer service centers, they know. Okay, I worked at an inbound telemarketing center at Sprint in the very early days, even before it was known as Sprint. And when an ad, remember, anybody seen the pin drop commercial? Okay, yes, that ad has been being used since 1988. And that ad was so successful that when that commercial came on TV, when there were only like, maybe 10 channels, okay, and half of them were fuzzy, right? So when that ad came out, we would get bombed with 1,000 calls, and we only had at one time, boom, just like that, maybe 5,000 calls, and we had 200 people on the phone. Well, 200 was the max we could do. So as a result, what did Sprint do? I mean, they were losing. They put you on hold. They can delay you coming in. There's a couple other things they can do. Hire more people. That's right. And so we would use those numbers to justify hiring more people. Okay? All right? And so you put it in your handy-dandy formula here, and you come out with 0.16. Okay? So and verify that. Now we have handy-dandy tables for Poisson as well on page 995. This, oh, by the way, this is the day we go normal time. 995 Poisson tables. Okay? And we're looking at what was the probability we're looking for the probability. Okay, the mu in this case was 4. No, was 3, and x was 4. So you look across those tables just like you did before. 3 for mu, right? Half hour, and x was equal to 4. Okay, and so you'll see that the probability, and this is where it's a really powerful tool for people who are trying to staff or you're trying to size the computer system here. Okay, if everybody tried to get on to the wireless network all at the same time, would everybody get on? That'd be a no. Okay, but some engineer at the university or some technical guy at the university has calculated these out, and so this says there's a 16% chance that you're going to get 4 people in during that half hour. All right. Now the interesting thing about this is that if you go down and you say, okay, well, what would the probability be that they would get 0 people? Okay, and we're going to extend this, going down the table. What's the probability for this emergency room that you would get 0 people in that half hour period? Would it be 0? No. What's it going to be? 0.0498. That's right. All right. And so then you can keep extending that. Okay. And then you get down here to what's the probability that 9 people are going to walk in to the emergency room at that time? Everybody see that on the table? 0.0027. That's right. That's right. Exactly. And now if you added all those up, if you went 1 to 12, because after 12 it becomes negligible, if you added all those up, you come dangerously close to 1.00. Okay? So now you're the hospital. What's the business decision here? Do what?
I would go with 1 doctor.
Why?
Stop that, because it's only a 16% chance. So,
Yeah, but if 10, but keep in mind that there is a cumulatively close to a, let's call it about 80% chance that 6 people are going to walk in. Cumulative probability, you see what I'm saying? Cumulative probability that about 80.8. Okay, and this is the decision. This is the mindset of the decision makers when they're trying to say, okay, should I staff up or should I just accept that, hey, more people are going to be waiting in line? Yes, sir. Shane. Oh, that's the value of E. Yeah, that's just E. It's kind of like a pi. It's like pi. Pi is 3.14. 14, and you can carry that out as many times as you want. E is equal to 2.718. Always. Always, always, always. Just like pi is always 3.14 something, something, something. Okay? And so this is how people staff up. This is how people decide how much equipment to put in. This is how they decide how many classrooms we need at the University of Cincinnati at any one time. What's the probability that they're going to get 15,000 people sign up for next semester instead of 10,000? And then you size your staff, faculty, rooms. The rooms are the rooms, but even there you have an option. What's the other option if you run out of rooms? Bump them online. Or you do a hybrid. Okay. And that's what this table is all about here. Okay, you can see that this is the number of arrivals is at about 6. At about 6, you're kind of wasting your time to staff up for any more people, for any more emergency room, because there's only like what, a 2-3% chance that you're going to get overloaded. All right.